Starting our fourth unit today. The title of the unit is The Wave Nature of Light. Some of you are going to have a little, I don't know, reflection back to grade 10. In grade 10 science, you did learn some optics, but the optics you learned in grade 10 is something that we call the ray model of light. It does a great job explaining reflection, transmission, absorption, so lenses, mirrors, colors. Um, Basically, all it says is that light travels through a medium in a straight line at a constant speed. The ray model doesn't work for other stuff, though. The ray model doesn't explain what we're going to talk about quite a bit this quadmester, and that's the interference of light. So we got to bump up, we got to talk about, we got to use a more complicated model, and the model we're going to use, sorry, is called the wave model. As I said, the wave model is the only way to explain diffraction and what we're going to do a lot of interference. To get to the wave model first, let's backtrack and make sure that waves make sense. Since it's been a while since grade 11, and depending how you learn grade 11, we maybe learned it in different models. So just to make sure waves is still okay in our head. In this little document, my animated GIF isn't animated, but if you look at it in the Google Doc, it's a cool wave animation. If we look, say, for example, this red dot right here, if you could focus your attention on that red dot, it's just wobbling up and down. So it goes down, then it goes back up over and over again. So that red dot's going up and down over and over again. That's a vibration. Any red dot that you could focus on. When I typed the note, I was looking at the first red dot. If we looked at the first red dot, the one here, it's doing just what I said, wobbling up and then back down over and over again. That's a vibration. What a wave is when this vibration, this first one, triggers the next dot to do the same thing. Then that triggers the next dot to do the same thing. That triggers the next dot to do the same thing. So there's a bit of a delay as it works through all these dots, but eventually every point in this material is wobbling up and down exactly the same. So it's one vibration triggering or causing the next piece of the medium, in this case the next dot, to vibrate. And then that vibration triggers the next one, and so on, and so on, and so on. That's what a wave is, a disturbance, so an input of energy, something shaking this first red dot up and down, but that energy gets transmitted through the other dots or the rest of the medium till eventually the last dot's wiggling up and down. That's what a wave is. In this particular one, the dots were vibrating up and down, but the energy was moving sideways or horizontally. We call that a transverse wave. In waves and sound in grade 11, we talked about sound as a longitudinal wave. We don't need to worry about that for wave optics, but that would be a different kind of wave. Before we get too much more, a couple little things I didn't type, but I'm going to mention out loud. When we do have a wave traveling, the length of one wave, we call it L for length, but regular L was used, so we use Greek letter L. So a wavelength is Greek letter L. I'm going to call it lambda. That's how I'm going to draw it. As something vibrates, it wobbles from sort of a resting or equilibrium position to way up here, and or from the resting position to way down there. Those distances measured from the resting position to the peak and the trough, those maximum distances, those I'm going to call A for amplitude. How quickly it wobbles up and down, we're going to call that frequency. So if I had a stopwatch watching this animation happen, frequency is how quickly it's wobbling up and down. And frequency connects to wavelength through something called the universal wave equation. We learned it in grade 11, V equals F lambda. There's a connection between F and lambda. A high frequency source creates a shorter wavelength, or a low frequency source creates a low wavelength. That'll all come up again, but just sort of file that away, grade 11 stuff that will come up again in grade 12. Okay, carrying on with our note. This is where it's going to get a little bit nutty. I'm going to try and explain how we make light. Again, mine's not animated, but in your Google Doc, so maybe have it open or pause this video and take a peek at it. Imagine that we had this mass, kind of like those red dots. Imagine that this mass on the end of a spring a nice little follow-up to simple harmonic motion. If I pulled the mass down and let go of it, it's going to go up and down over and over and over again. It's going to have a particular frequency and a particular amplitude for what we're doing. I don't really care about that, but look at the GIF if you haven't yet. If we have a mass on the end of a spring, it can wobble up and down. As it wobbles up and down, let's say we start looking at it when it's at the very, very bottom of its vibration. It moves upward, but for the first half of moving upward, it's actually getting faster. So it accelerates upward for the first little bit, gets to its equilibrium, then it still moves upward, but for that next half of moving upward, it slows down and stops at the top. So on the way up, it starts off at rest, gets faster, 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 till here, then gets slower, 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 till there. Then it turns around and does kind of the same thing in reverse. It starts off slow, accelerates to a speed on the way down, then slows down and stops at the bottom. So on the way down, at the top it goes faster, 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 so it's going fast here, and then slow down, slow down, slow down, stop when it gets to the bottom. So as this mass wobbles up and down over and over again, simple harmonic motion, we know that the speed basically follows a sine curve. If we start tracking it when it's at the bottom, it starts off not moving, accelerates to that equilibrium position, then keeps going upward but slows down, then turns around and accelerates, then slows down and stops, then turns around, accelerates, slows down and stops. So it's got this repetitive speeding up, slowing down, turning around thing that's going on. Okay, now here's the cool part. What if instead of a mass on a spring, or maybe it is a mass on a spring, but we somehow make it positive? So kind of like rubbing a balloon on our hair or something, we rub this mass on something and we give it we take away a bunch of its electrons so it becomes positively charged. From what we just did in the last unit, we're not going to do the equations for it, but what we just did in the last unit is if you have a moving charge, the moving charge creates a magnetic field. So this isn't like electricity in a wire, but it's kind of behaving like it. We've got a positive charge that moves upward, then we've got a positive charge that moves downward. It's not in a wire, but we can apply our right-hand rule for straight conductors, and we can figure out the direction of the magnetic field that's created around this wobbling charge. It's tricky to type this, so I've got some words there. Remember, this would be happening in 3D in all sorts of directions around the wobbling mass, but to try and type it, I just focused on what was happening exactly to the right of the charged object. So if we go back to this little diagram, I imagined what's happening to the magnetic field kind of over here. The magnetic field would also exist in front of the mass, behind the mass, to the left of the mass, but just to try and get through this as easily as possible, let's just focus on what's happening to the right of that moving charge. If we start with the mass at the bottom and that it's moving upward, do right-hand rule for that. So I'm saying it's positive, so we're using our right hand. Point your thumb matching the direction that the charge is moving. So take your right thumb and point it upward. When you point your right thumb upward, look at the curl of your fingers. And as I said, to just try and simplify it, what's going on to the right of the wire? So looking at the curl of your right hand, I can't do multi-screen to show you what your hand should look like, but stick your thumb in the air. You should get your fingers are kind of pointing towards you on the left of the wire and away from you or into the page on the right of the wire. So in this space over here, that little purple box, I know that the magnetic field is pointing away. We draw a pointing away magnetic field as X's. So there'd be a magnetic field over there that is away from you, or drawn as an X. The mass moves upward, but it changes speed as it goes. It speeds up for a little bit. That means we're going to have an X that's getting bigger and bigger and bigger, and then it slows down. That means our X is going to get smaller and smaller and smaller. Then the mass literally stops for a split second, so the X disappears. Then the charge starts to move downward. So we should do the same thing, right-hand rule, but this time point your thumb downward. When the mass is on its way downward, right-hand rule, on the right-hand side, the magnetic field would be coming towards you, or I would draw that as a dot. As it comes downward, it's making a magnetic field on the right-hand side, that's a dot, And as it comes downward, the first thing it does is it speeds up. So as it speeds up on that first part of the way down, the dot gets bigger and bigger and bigger, stronger and stronger. Then it starts to slow down. So the dot's still there, but the dot gets smaller and smaller, or weaker and weaker. Then it just cycles through that all over again. Then it starts going up again. So as it goes up, our dot gets replaced with an X. The X starts off small, gets bigger, then weakens again and disappears at the very top. Then when the mass comes down, the X gets replaced with a dot. On the way down, it's a dot that gets bigger for the first part. As the mass slows down, it gets smaller. So it disappears again, then it switches back to an X. So basically, this is a little bit weird, but at this spot right here, if we could see magnetic fields, the magnetic field would be kind of following a sine curve as well, going from X's to big X's to small X's to small dots to big dots to small dots. So it would be cycling through all these magnetic field values, just a smooth transition from small x to big X to small dot to big dot to small dot. So it would just be cycling through all those, kind of like a vibration, kind of like the mass is wobbling up and down. We've got a magnetic field wobbling. It just happens to be wobbling as dots and X's. Oops, that's all typed in here. If we could see the magnetic field, we would see it changing back and forth from dots to X's. It would be vibrating as well, just dots and X's. All right, here's where it gets weird. What we kind of run out of time for in grade 12, and because our math isn't so strong, it's a good thing to leave off till your calculus gets better. But we've just said that a moving charge triggers a magnetic field. The flip-flop is opposite as well. A changing magnetic field can create electricity, can create charge. If we had more time and wanted to talk a little bit about induction, that's what this guy named Faraday and this guy named Lenz worked on, we can use magnetisms to make electricity. Or more fundamentally, a changing or vibrating magnetic field creates an electric field. So what we've got is our wobbling charge, this mass going up and down over and over and over again. It's going to create a magnetic field kind of to the right in what I drew as a purple box that happens to be changing over and over and over again in the form of dots to X's, X's to dots over and over and over again. What we didn't get to in our field theory is that that sort of behavior, a vibrating magnetic field, is going to create a vibrating electric field. So the moving mass created a magnetic field. The magnetic field is going to create an electric field. Since our magnetic field is flip-flopping dots and X's, that's going to create an electric field that flip-flops vertically, kind of like the original charge. It's going to be flip-flopping up and down. So I'm going to skip those next couple words. I'm going to go down to this next image. If I go like this, shrink it a little bit. There we go. From what we've said, the moving charge in this spot is going to create a magnetic field that's kind of alternating between X's and dots. So this change happens over time. X to dot, dot back to X. So if we could see magnetic field, we'd see a flip-flopping of dots and X's. What magnetic field theory says, what we didn't get to, is this changing magnetic field induces a changing electric field. Again, it would be in all directions, but if we just focus on what's happening to the right, the magnetic field of dots and X's changing over and over again is going to make an electric field here that's flip-flopping from up to down over and over again. So this mass was wobbling up and down. It created dots and X's wobbling in the magnetic field beside it. The dots and X's of the magnetic field trigger an electric field. Here, let's do it a little bit better. I'll make the magnetic field another color. Sorry, the electric field is in green now. That changing electric field, fundamentally, as far as magnetism is concerned, that changing electric field looks exactly like a current. So that's going to trigger a changing magnetic field. If we keep going to the right, it's going to trigger a changing magnetic field that alternates between dots and X's. Now we've got a repetition thing going. The charge created a magnetic field, but the wobbling magnetic field created this wobbling electric field. This wobbling electric field creates a wobbling magnetic field. That kind of looks like where we started. That wobbling magnetic field creates a wobbling electric field, and so on, and so on, and so on. It's all typed up here, but it's basically one changing, creating another. The charge created a magnetic field. The magnetic field created an electric field. That electric field creates a magnetic field. That magnetic field creates an electric field. That electric field creates a magnetic field, and so on, and so on, and so on. It's a little bit weirder, but that's exactly how I talked about how we make transverse waves. The first dot triggers the next dot to wobble. That dot triggers the next dot to wobble. That dot triggers the next dot to wobble, and so on, and so on, and so on. This one's more complicated, but what we've done, if we could take a charge and shake it up and down, wobble it up and down, literally attach it to a spring, or if we could get rid of the spring and attach like your arm muscle and just shake it up and down with your hand, the wobbling charge creates a wobbling magnetic field. The wobbling magnetic field creates an electric field. The wobbling electric creates a magnetic. That creates an electric, and so on, and so on, and so on. So we get this rippling of electric and magnetic fields leaving our vibrating charged object. This one, again, it's not animated on my screen, but this one's a little bit rougher. But if you look back at the Google Doc, way back here, kind of in red, is their charge, and it's wobbling up and down. As it wobbles up and down, it creates an oscillating magnetic field. They've chosen to use yellow for their magnetic field, and it's dots and X's. So the animation does an okay job of showing it, but the magnetic field wobbles out of the page and then back into the page and back, out of the page and back. So the magnetic field is perpendicular to what the charge is doing. The electric field wobbles up and then, oops, can't see that one, wobbles up and then back down. Then it flips down and then back up, up and then back down. So this wobbling charge triggers two things: a wobbling magnetic field, which happens to be perpendicular, and a wobbling electric field, which happens to be parallel. Like if the charge is going up and down, then the electric field is also up down. This is one model of how we can make light. If we shake that charge and we shake it at the right frequency, depending on the frequency, like what I mentioned earlier, V equals F lambda, each frequency has a particular wavelength. If we get the frequency right so that we get the wavelength just right, then our human eyeballs have evolved to respond to those electromagnetic waves. If we shake it at just the right frequency to create just the right wavelength, and if it falls in this really narrow window in here, it's blown up down here, then shaking that mass up and down with shaking a charged object up and down will create electromagnetic waves, basically, that we're going to call light. There's a whole bunch of electromagnetic waves. If we shake it slow, we're going to make really long waves like radio waves. If we shake it faster, we're going to make things like gamma rays or X-rays. And if we shake it at sort of the just right speed, we're going to make what we call visible light. Our eyeballs, give or take, respond to 400 nanometers to 700 nanometers of wavelength. The shorter ones are more purpley or violet. The longer ones are more red. But that's our spectrum. If you shook it slower, the longer wavelengths trickle out into radio waves. The shorter wavelengths go ultraviolet into X-rays, or sorry, infrareds in there as well. That's one way to make light. Shake a charge up and down, and as you shake that charge up and down, it creates these EM waves, and if they're in the right range, our eyeball detects them. Old school AM, FM radio, they just shake charges up and down. In the radio broadcasting, they literally connect it to a power source and shake electrons up and down so that it creates waves in these longer ranges. There's lots of ways to create light. This is just going to help us later to wrap our brain around why light does some cool things like interfere and this diffraction thing, but mainly interference is what we'll get to. So bottom line is, read through this slowly. We're going to model light as an electromagnetic wave. There are vibrations in both the electric and the magnetic fields. Those vibrations happen to be perpendicular to each other. How quickly they vibrate depends on the source of what creates that wave in the first place. Once we have that source shaking up and down at a particular frequency, that's going to cause energy to ripple forward. Just like we talked about in grade 11, the speed of a wave depends on the medium. Most often we're going to be working in air or a vacuum, and the speed of light in air or vacuum is the 3 times 10 to the 8 number. In grade 10 optics, you talked about like index of refraction. In other transparent materials, light goes a little bit slower. We won't really need that this year. It'll come up a little bit later, but not a big deal. Since light is a vibration in fields and not actually a material like air, air is vibrations of particles, or sorry, sound is vibration of air particles. Sound can't travel through a vacuum since there's nothing, no particles to vibrate. Since light is this weird vibration of the fields, it doesn't need a material. They can just shoot through a vacuum. There's all sorts of ways to make light. I'm going to talk about, I like this EM wave thing because it helps us visualize the crests and troughs that we'll need for interference. There's other sorts of ways. LEDs is a way to make light. Gas emission, like you might have seen in chemistry, makes light. Basically electrocute a gas and it gives off light. Lots of different ways. I'm going to pause the video here before it gets too long, but take a look at example 1. It's really a grade 11 question. If I give you a lambda and a V, you should be able to calculate an F. I'm going to pause the video and then we'll talk a little bit about polarized light and we'll keep on cruising.